Okay, let's get started. Last week we learned the instructions and directives. So here are the definition of directives. Directives are not instructions. So these are not really converted into the binary. These are some of the commands that understood by the compiler or assemblers. Okay? As an example, see here that you see CSEG or code segment at 1000H, which basically means that you want to start the code segment at 1000H. 1000H is going to be the base address for your code segment. Okay, that's all this line or says. Right? This is not instruction. These are not really changed to binary, converted to binary. SP data 0x81. This one also means that SP means 0x81. And this one also, limit is a name of constant. Okay? So limit equals to 2000. Okay? That's what it means. So these are not really instructions. We are not really moving any value, or we are not adding something. This is just a definition. Look at the C function. You have a hash define, right? This is the same as hash define. Same here. Same here. Okay? So hash define is not instruction. Even in C language, those are not really compiled to a binary. Same here. These are called the directives. We learned the instructions last week, and there are 5 different groups in instructions. First, the data transfer, arithmetic, logic operations, Boolean, branching, and we're going to look at one by one. First of all, data transfer. Move instruction is probably the basic one for data transfer instructions. And there are also exchange instructions where you exchange the value in 2 different, in this case, the register and the address, right? So you are changing these 2 different values. And move instruction is copy the value in the source to the destination. These are arithmetic instructions. You have add, and in case of add, you have add C also, which means that you are adding these 2, and the result of the addition goes back to A, accumulator, plus C in this case. Okay? You also consider carry. Okay? In addition to the adding these 2, you also add carry. Sub B, this one is a subtract with borrow. Okay, the reason that we have a borrow always in subtraction is because that sometimes, right, you want to probably subtract from small value to large value. So in this case, you do like A minus byte, and the result go back to A. But sometimes A can be a smaller value than this one. Okay, in that case, the value is going to be negative. Right? But we cannot have a negative here, so therefore we have to do borrowing. So whenever you do a borrowing, you'll have a carry flag up, right? Right? This one is an increment, decrement. Increment the value in here, decrement the value in this address. Multiplication, division, and this is a data decimal adjust. We'll look at a little bit detail in the next slide. So whenever you do the arithmetic instructions, right, the value in here in program status word is going to be changed. The values here, the bits, especially the carry bits, auxiliary carry, overflow, and also parity. These 4 bits are always changing. Okay? Every time you do instructions, they run each of these instructions, these 4 bits are changing. Okay? And you need to understand how those are changed. There are also other types, so logic instruction, and, or, logical or operation, exclusive or, complement. Okay? And also, we learned that to clear and rotate left with carry, rotate right with carry. Let's look at some of those things. So rotate left in this case means that you are rotating, right? So each bit is moving towards the left. And this one, the leftmost bit, is going back to the end. Okay? That's rotate left. And rotate right, they're rotating in clockwise. This case is counterclockwise. So they move the clockwise in rotate right. So the last one, LSB, they go back to the front. It's going to be MSB, most significant bit. If you want, then you can do rotate right with the carry. In that case, since we consider carry, you put the carry here and make a 9 bits. And with the 9 bits, you are doing rotation to certain direction. In this case, it's toward the right direction. So 9 bits, you're doing rotation like this. Okay, so that's the what's happening. And remember that generally this is one of the reasons why you want to do the rotate. Look at this one. This is the case with the RLC. Okay, we have a carry. And we are doing rotation to the left. So it's case of RLC, like this, right? And whenever you do RLC, so they are moving, each one of the bits is moving 1 bit, shift to the left, right? Every time you do, mathematically, it's basically same as multiply by 2. Okay? Every time you run this, mathematically, it's same as times by 2. Okay? Multiply by 2. Similarly, whenever you do rotation to the right, okay, RRC or RR, for example, right? In this case, it's RRC. Okay, whenever you move the value to the right by 1 bit, it's the same as divide by 2. Okay, so that's this is the most popular reason why you want to use RLC and RRC. Okay, today, what we're going to look at is flow control, program flow control. So what this means is program typically runs from a lower address down to the higher address, actually going that way, if you like, right? So you are starting from, for example, 0, 0, 0, 0, okay? And the program goes down to 0, 0, 0, 1, 0, 0, 0, 2, okay? So the address is incremented, okay? So that's typically a flow. However, in some cases, right, for example, jump, okay? In case of jump, now you are executing 0, 0, 1, 0, and the next instruction may not be 0, 0, 1, 1, because maybe the instruction now is a jump, so you suddenly jump to somewhere else, right? You are not really going down to the next address. So that's a flow control. You are basically suddenly jumps to somewhere else. Okay? So for example, jumps. And there are 2 different jumps, unconditional jump and conditional jump. So unconditional jump basically means that it's the same as go to. So whenever you reach here and whenever you see the unconditional jump instruction, then you have to jump. No matter what, you're going to jump. Okay? No condition. Okay? Whenever you see jump, unconditional jump, you're going to jump. Okay? That's unconditional jump. Second case is the conditional jump. What this means is that you are going to do jumping only when your condition is met. Okay? Only you have certain condition, then jump. It's not always jump. Okay? This is always jump. This one, you're going to jump only when your condition is met. Okay? We'll look at it more detail. There are other type of jumps. For example, subroutines. This one is almost the same as jump in a certain sense. But we do not call this a jump. Instead, we call this, we say this one is a call and return. Okay, this one is a jump. This one is a call and return. So we'll see the difference. First of all, unconditional jumps. This is the easiest way, the simplest one. Let's look at the instructions. S jump. Okay, this is one of the unconditional jump instructions. S jump. S means short. J and P means jump. Okay, short jump. So what does it mean? here, actually, look at here. There's another one called L jump. L means a long jump. This is a short jump. This is long jump. Okay? But anyway, these are unconditional jump. What is short jump basically means that let's say you are executing instructions one by one. Okay? And suddenly you see the S jump instruction. In that case, you're going to jump, but your jump is short jump, right? So you are going to jump within a short range. So here, the range is that you can jump forward. Only the maximum jump you can have to the forward direction is 127 byte. And you can even, sometimes you can jump back, okay? These are the sequences you are moving towards down, and sometimes you can jump back. Maximum is it's 128. So it's like plus 127 or minus 128. That's the range of your jump. So in this case, look at here. This one is a relative address. So what this means, it's not an absolute address. It is relative address. What this means is that, let's say you, let's see an example. Let's look at a very basic assembly. Okay, assembly code. In this case, right, what I'm doing is that I have some of the instructions, and later I have a short jump, and I put the label L1. In that case, right, this is unconditional jump. So you execute this line, and later you execute this instruction, and go down here. And when you execute this instruction, what happens is you're going to jump back. Okay? That's what it is, right? Jump to L1. It's jump back. Okay? But here, right? The range, so this is your current, when you execute this line, this instruction, you are currently right here. Okay? Since you are executing this one. So compared to your current position, current address, how much further you can jump, or how much you can jump back. So these are the range. But in this case, this is in case of short jump instruction, the address here is relative address. See here, relative address, which means that compared to your current line, current address, you can jump back, which is going to be minus, let's say minus some value, minus 10, for example. And if you move forward, when you jump forward, let's see that in some other cases, you may have a L2, right? In that case, you are jumping forward. In that case, the value, operand, you're going to have a positive value. So positive means jump forward, negative means jump back. Okay? But think about this one. When you have operand, this operand is going to be 8 bits. This is 8-bit. The OP code is 8-bit. You have a one operand in this case. One operand is another 8-bit. Since you have only 8-bit for this operand, okay? And this is 8-bit. And in this case, you need to go sometimes you need to go back or go forward, jump forward. We have to use a sign value, okay? Sometimes we can have minus or sometimes plus. So what's the range that what is the range of the value you can have? Using 2's complement, you can have maximum 127 and minimum minus 128. So which means that you can jump back, but this is the maximum you can jump back. You cannot jump like 1,000 back. Okay? This is the maximum range you can jump back. And 127 is the maximum range you can jump forward. You cannot jump to like 200. You cannot do that. Okay? This is the only range. This is why we call this a short jump. You are actually jumping in both directions, but you are jumping within a short range. Okay? So that's a short jump. One thing to remember actually is that what is this number? Let's say you are jumping forward and I'm jumping plus 2. So what does it mean? Plus 2 means what? What's the unit of this? This is not number of instructions. Okay? Plus 2 does not mean that you are jumping to the 2 instructions, okay, forward. You are not moving to this one in this case. Okay? 2 does not mean the 2 instructions. Then what does it mean? 2 means byte address. Okay? You are jumping to another location with the plus 2 address. Okay? You have a certain address here, okay? And you are jumping to another address, but that address is my current address plus 2. Okay? And let's say I'm jumping to minus 10. That basically means that my current address is, for example, some in decimal value, okay, in decimal. Let's say my current address is 100. And when I have minus 10 here as an operand, that basically means that I'm jumping back to address 90. That's what they mean. Okay? This is not the number of instructions. This is the number of bytes. Okay? That's one thing that you want to remember. Okay? And another thing. Okay, so this is a byte address, as I said, right? So plus 2 basically means that you are adding plus 2 from the current address, and you are jumping to that address. Then, what's the difference between the 2 instructions and 2 bytes address? Or maybe, let me ask a question in another way. Let's look at these instructions. How many bytes do you need for this instruction? I'm talking about only one instruction. We are looking at only one instruction, move instruction, right? How many bytes do you need for this one? In this particular case, right? In this particular instruction, you need 2 bytes. One byte for this instruction, but the move R0, this whole thing is 1 byte. Okay? The second byte, this one. So you need 2 bytes. Okay? Actually, these instructions are very simple instructions. So all of these things actually need only 2 bytes. Each of them is only 2 bytes. But there are some other instructions. For example, right, we'll see later, but there are some complex instructions. For example, conditional jump. In that case, sometimes you need to compare this value with another value, and if those 2 values are same, then you're going to jump to somewhere else. So you may have multiple operands for some instructions. In that case, that particular instruction probably is like 3 bytes or 4 bytes. Okay? This is a simple instruction. That's why you need only 2 bytes. For some other instruction, maybe you have 3 or 4 bytes. So in that case, right? Now, going back to this one, let's say I want to jump to somewhere else with the plus 2. Then what's going to be happening in this case? It's most likely it's a 1 instruction, right? Assuming that in 1 instruction is only 2 bytes. If the next instruction is this one, for example, when I say plus 2, that means one instruction. If I have plus 4, and each instruction only is 2 bytes, then plus 4 basically means 2 instructions. Okay? So this is not the number of instructions. Okay? That's one thing you want to remember. So here, this relative address, this is the operand. This one, you can have, the value you have is from minus the positive 127 down to minus 128. So depending on this negative or positive, you can jump forward or jump back. Okay, so that's one thing to remember. And the reason that why we call this as a relative address is because that compared to your current address, you're going to jump forward, jump back. And long jump, okay, this is long jump. In this case, long jump, you are using absolute address. This is not relative address. Okay, this is a absolute address. And this address actually is 16-bit. That's why we call this long jump. In this case, long jump, right? You can have 16-bit address. Okay, so what is the range of this jump? This case, right, the range is only 256 bytes, right? Because we have only 8-bit. In this case, what's the range of your jump? We have a 16-bit address, right? So the range of the jump you can have with the long jump is 64K. And what is our address space? 64K. Okay? So which means that this one can jump anywhere. You have a 64K of address space, and with this command, you can jump to any place, any address. So therefore, in this case, you don't have to have a relative address. Okay? You can just have absolute address. So in this case, long jump, I have 1000H, then you jump to 1000H. This is not a relative address. Okay? You are jumping to this actual address. So that's long jump. Okay? 16-bit. There's a third one called absolute jump, A jump. In this case, it's a little bit different. In A jump, okay, in the previous short jump, you have 8-bit address. Okay? That's relative address. And long jump, you're using 16 bits. Okay? So that's the total number of address space. And in this case, A jump, you are using 11 bits. Somehow it's like between short jump and long jump. In this case, you are using 11 bits of address. And how much space can you, what is the range for 11 bits address? Let's say you have 11 bits. Then how much space, address space can you have with 11 bits? 2K. Okay? 2K. 11 bits is 2K. Why is that? 10 bits is a 2 to the 10, 2 to the power 10, which is 1K. Okay? But 11 means 2K. So 11 bits is a 2K. And how do you make 11 bits? We have 2 bytes. This is, again, this instruction is a 2-byte instruction. We have only 2 bytes. So here are 2 bytes, right? The second byte here is operand. We have 8 bits here. That's operand. And interestingly, this instruction has additional 5 bits here, additional 3 bits here as operand. Okay? So this one has the first byte, like this one, second byte here. And first byte, we have 8 bits, right? And out of these 8 bits, the last 5 bits are only OP code. The first 3 bits and the second byte, which is 8 bits. Put them together, 8 bits here, 3 bits here, adding together, it's going to be 11 bits. These 11 bits will be your address. Okay? That's your address. So therefore, in this case, it's going to be 11 bits address. So what does that mean here? Okay? For other instructions, right, typically the first byte is OP code. Okay, first byte is OP code, generally. In fact, this one you can actually think the same way. The first 3 bits is part of your address. So now let's pick an example. Let's say we have 0, 0, 0 as an example. Okay, 0, 0, 0. In this case, what would be the number for this first byte? 0, 0, 0, 0. 0, 0, 0, 1, so it's 0, 1. like this, right? And let's say, as an example, let's pick the second one as a 62. Hey, H. Actually, this is H here. Okay, 62H. Okay, in that case, we pick the 62 here. And first one, let's say we have 0, 0, 0. Then it's going to be 0, 1, 6, 2. Okay? And let's say we have 0, 0, 1 here. Okay? For these 3 bytes, 0, 0, 1. In that case, the first byte is going to be 2, 1 and 62, which is this one. Okay? So depending on the what value you have in these 3 bits, maybe you have a different one, right? You can have different one, right? If you have a 0, 0, 0 for 3 bytes, it's going to be 0, 1. If you have a 0, 0, 1, it's going to be 22, 21. If you have a 1, 1, 1, then it's going to be E1, which is this one, right? So now what this basically means is when you see a jump instruction, okay, when you convert this a jump instruction to the binary, okay, what I'm talking about is assembler. Okay, when you run the assembler, assembler converts this instruction to binary. When you convert this one to binary, there are 8 different choices. A jump can be mapped, can be converted into one of these 8. A jump sometimes can be 0, 1, sometimes can be 2, 1, sometimes can be E1. This is the instruction map I show you, right? Let's see here. 0, 1, A jump, right? 2, 1, A jump again. 4, 1, A jump. 6, 1, A jump. Okay? There are 4 more there. A jump, A1, E1, something like this, right? There are 4 others. Each of these is jump, A jump. So whenever you see an A jump instruction can be, when this is converted to binary, sometimes it will be converted to 0, 1, or sometimes 2, 1, 4, 1, 6, 1, something like that. But here you see that this one is a P0, P1, P2. What is a P1, P2? No, this is not port. This is the page. We are not talking about port here. We are talking about page, the concept of page here. See the, here. 0, 1 is for page 0. 2, 1 is for page 1. So here's the concept of page. What this means is that let's say this is the whole memory space from 0, 0, 0, 0 to FF, right? This is a 64K of total, the whole address map. In this address map, maybe your code is somewhere here, okay? And right now, you have a lot of instructions here and you execute line by line. And at a particular time, your program counter is indicating this one, which means that this is the next OP code that you are running. You are actually executing instruction right before that, okay? That's the instruction you are now executing, okay? And now let's say the current instruction is, say, A jump 62 as an example. Let's pick an example. In that case, what this means is that we are thinking as a 2K of range. Within this range, we are dividing this 2K into 8 different pages. We have a 2K right here, and this 2K will be divided into 8 different pages. This is a page 0. Page 1, 2, 3, 4, 5, 6, 7. Okay? We are dividing this 2K divide this 2K into 8 different pages. Once you do that, then each page is going to be 256 bytes. each page is only 256 bytes, right? And we have 8 different pages. So when you look at here, right, we have 8 bits here. These 8 bits, with these 8 bits from A0 to A7, now you can see that within this one page, which address you want to jump to. So this one, this 8 bits basically tells you that, let me put it this way. The first 3 bits, in this case actually, it's the most significant 3 bits. These 3 bits will tell you which page you want to jump to. Maybe you can jump to page 0, or maybe you can jump to page 5. Okay? Which page you want to jump. Okay? These 3 bits will tell you which page you want to jump, and the remaining 8 bits will tell you within that page which address you are going to jump to. That's what you can do with the A jump. Simply speaking, right? Simply speaking, our range, the range for jumping is 2K. This is our range, 2K of jumping range. For this 2K jumping range, we divide this one into 8 different pages. Each page is only 256 bytes, right? And using these first 3 bits, using these 3 bits, you find out which page you want to jump. If those 3 bits, for example, as 0, 0, 0, then what that means is I'm going to jump to page 0. If this one is 1, 1, 1, then I want to jump to page 7. But this page still has 256 bytes, right? So even though you have 1, 1, 1 here, I know that I'm going to jump to page 7, but I don't know which one exactly that I want to jump to, because in page 7 we still have 256 bytes. So using the remaining 8 bits, now we want to find out which one exactly we want to jump to. With 8 bits, now you can have a 256 value, right? Okay, so this one tells you which page you want to jump. And this one, 8 bits, will tell you within that page, okay, which address exactly you want to jump to. Okay, so that's what you're doing here with A jump. Simply speaking, short jump, you are jumping within a very short range, 256 bytes. Long jump, you can jump anywhere, 64K of range. A jump, you have 2K of jumping range. Okay, so that's the difference. But the common thing is that all these 3 are unconditional jump. Whenever you see this one, you have to jump. These are examples. Let's see your code segment at 1000H. So your code starts at 1000H. That's what this means, right? Directives. You execute the copy of 03 to A. And copy that value into port 1. When you see this long jump 1000H, this is unconditional jump. So you have to jump to 1000H suddenly. Okay. This is another example. Same here, pretty much. The only difference is that instead of long jump 1000H, what I'm doing is the short jump loop. So look at these 2 programs. Let's say when you run this program in one machine, and let's say you run this program in another machine. So what would be the difference? Let's say you run 2 different programs in 2 different machines. Do you see any difference? No, I mean let's say you compile this and run in the microprocessor. These 2 will be exactly the same. These 2 will be exactly the same, right? From the microprocessor perspective, these 2 are same. Why is it same? Let's look at this one. This one looks easier. You execute this one, and now you want to do short jump to loop. And loop is right here. So you jump back to here. and going this way and jump it again. It's like an infinite loop, right? But whenever you have here, it's going to be short jump to loop, so you do a short jump. In this case, the range between this one and this one is less than minus 128, right? So definitely no problem. Okay, distance between these two should be less than 128, right? Because this is a short jump, but this is pretty close, so you can do short jump, no problem. Let's see this one. Now what I want to do is a long jump, but I want to jump to 1000 H. Suddenly I want to jump to 1000 H. But where is the 1000 H? 1000 H is here, actually. Why? Because I said this one. I said my code segment start at 1000 H. So this is actually 1000 H. So because of the directive, I define that way. This is my 1000 H. So when I say 1000 H, it actually means this one. So I just jump back to this. So these are identical. However, which one is a better code? This one is definitely a better code. We typically call this relocatable code. This one is a non-relocatable. What does that mean? Relocatable means that, let's say for some reason later I want to change this value. Right now here, this is my code, and by specifying these directives, I want to load this one into 1000H. I have a 64K address map, but this out of this 64K address, I want to locate this one into 1000H. That's what this means, right? But later I change my mind, and I want to put my program into 2000H. Okay, I just change it. So in that case, I want to change this one into 2000, right? And this code runs no problem, same exactly as it is before. However, in this case, right, if you change this 2000, then this address is going to be now 2000. In that case, suddenly this one has to jump to 1000, and 1000 there's nothing. So this one will be down. The program will be down, right? So this kind of thing, right? You don't want to write the actual address value like this. This is a very bad way of doing it. Okay? This is very bad. So this is not relocatable code, and you don't want to do this. This is one of the reasons why we need label. Okay? You want to use label here. And another thing, short jump, you need 8-bit operand. Because we are doing short jump anyway. So short jump, we are jumping within the range of 256 bytes. So the operand is only 1 byte. However, long jump, you need 16-bit. Okay? So you have a 2 bytes. So this instruction, long jump 1000H, this instruction needs 3 bytes. This one, 2 bytes. Okay? So this one, 3 bytes. So generally, I mean, this is not good that way. Let's look at conditional jump. In conditional jump, you're going to jump under a certain condition. Okay? Only when your condition is met, you're going to jump. So let's look at some examples. J means jump. Z means 0. 0. Okay? So JZ relative address means that you're going to jump only when 0. Where? This address. Relative address. In this case also it's like a relative address. Same as like a short jump. Okay? Compared to your current address, you are going to jump either forward or backward. Okay, same as before. You're going to use a relative address, but the condition here is a 0. And which one is a 0? Accumulator. So this instruction is like jump only if a accumulator value is 0. JNZ, not 0, right? If accumulator is not 0, then you jump. JC, C means carry. When you have a carry set, carry equal to 1, then jump. not carry. When you have not carry equals to not 1, meaning the C carry equal to 0, then jump. Okay, that's J and C. Okay, JB, B means byte. You're going to do jump only when this byte is 1, like this. Only this bit is 1. And where to jump? This relative address. So in this case, right, look at this one. JZ, JC. In this case, you need only one operand. So this operand tells you where to jump. And in this case, we are basically looking at accumulator, and also we are looking at carry. So we know where is the accumulator and carry. So it's like a simple instruction. However, in this case, JB, what we are trying to do is we are trying to look at this particular bit address. If this bit address is 1, this bit is 1, then you jump to this one. So what this means is you need one more operand. We need 2 operands. We first go to this address and look at the bit. If this one is 1, then you jump to relative address. So you need 2 operands. Similarly here, J and B means not that this byte is not 1. Then you jump. JBC, what is it? In this case, C actually means clear. For this particular one, this one C means carry, but this one is clear. So this one means that J, look at here, J, if a bit equal to 1, jump if a bit equal to 1 and clear the bit. This one is nothing but just this one plus clear. Okay? You can run actually this one, and on the next instruction you can do clear bit. Okay? So combining those 2 instructions, it's going to be same as this one. So this one is simply adding those 2 instructions into one. Okay? There are more complex. There's a little bit more complex instructions here. These are actually a little bit complex instructions. Let's see. C. C means compare. Compare, jump, not, equal. Okay? E means equal. Equal, not, jump, compare. So let's see. We want to compare the accumulator with this. Okay? We want to compare these 2. In this case, you have 3 operands, right? 3. So 3 operands. You want to compare this one with this one. And when you compare these 2, and if those 2 are not equal, then jump. Jump to this one. This one and this one actually same. So the compare, jump, not equal. If A is not same as data, in this case the data, you see that you have a hash key, right? So this one is the direct address, not the immediate value. So if A is not the same as the immediate value, then you jump to relative address. Same thing here. If the R0 or R1, those register value are not the same as this one, then you jump. This is the indirect address. If the value in this indirect address is not the same as this one, then you jump. Okay? So those are pretty much same. The last one here, D. D means decrement. Decrement. You're reducing. Decrement and jump. J means jump. Not 0. So let's see what that means. The DJ and Z has 2 operands. First one is, let's say, R0 or R1, something like this. So if this value R0, actually you first decrement the value in R0. Okay? First you decrement this, and later you compare this value. If that is not 0, then you jump. So you first decrement this value. So this is the one. Simply speaking, This one, let's say you have this instruction, DJNZ R0 label 1. What this means is that in C language, for example, right? What you're doing is that you first do this one. This means the decrement. And then if this is what this means, right? You first decrement. And after you decrement, if the R0 is not 0, we have NZ, right? Not 0, then you jump. Okay? You combine all these things, just one instruction for all these things. Same thing for the last one, DJNZ IRAM. The reason that I say IRAM address is that this is the internal RAM. Internal RAM. Okay, internal RAM, but basically same as the address, internal address. So the value in here, internal address, will be decremented first. And if that value, after you decrement, if the value is not 0, then you do jump to relative address. Let's see examples. This is one example. Let's see, you copy the 03 into R0. And let's clear value in accumulator. Actually, by the way, speaking of clear, maybe in the midterm or maybe final exam later. Actually, last year, one of the question was to ask you to write a code. Okay, assembly code. And whenever you write assembly code, you have to remember that if you need the value A somewhere, for example, right, in your code, you are going to do this, right? Then you need to make sure that you clear the value. Okay? Let's make sure that, okay? Let's say you write a C function. Okay? When you write your C function, you always clear the value before using the value, right? Before using the variable. Same here. You have to clear the value first, and then later you're going to use it whenever you write the code. Okay? Okay, here, let's say I copy the 03 into R0 and I clear the value in A. Let's add accumulator with R0. Then R0 plus 0, that goes back to A. So A will now have a 03. Then I run DJ and Z. And R0, I have a 03. So when I run this, then what happens is I decrement R0 first. So R0 value is now 02 because I decremented. And compare that if that is non-zero. That's non-zero, right? Because we have a 02. So you loop. So go back here. And adding again. And A, what value did we have? 03. And now we are adding again. Then what's going to be the now new value of A? 05. Previous 03, and now we went back with the value of 02 in R0. So we are adding those two, 03, 02. New value is 05. And go back down here, and we again decrement it. Now it's going to be 01. Still not 0. Jump back. We are adding it again. Now what's going to be new value? 06. Down here, we decrement it. Now it's going to be 0. So pass. That's the simple program. Okay? In C code, like this. Okay? C code. Let's look at the call and return. So far, in jump instruction, what we have so far is that you have some instruction like this, right? You have add, move, whatever instruction you have, and suddenly you have short jump, or maybe long jump, or sometimes you may have a conditional jump, like a JZ, something like this, right? But whenever you have jump, either conditional jump or unconditional jump, when you jump, then this is your new instruction, and you just keep going from there, right? You keep just going from there. You are not going to come back because you jump. That's it, right? You are starting here. That's the jump. However, in call and return, difference is that in this function, this is almost same as jump. Difference is that you're going to return. That's a difference. Let's say instead of jump instruction here, now let's say we do call. Call. Maybe call label. Label 1. Something like this, right? And let's say somewhere else we have a label 1. And you have another instruction here. In that case, we execute this one, and this one, and this one. And when you execute this one, this is a call instruction, and call label 1. So suddenly you jump to label 1. So it's almost same as jump. But in this case, at the end of your label function, you have return. So you execute line by line in here until you see return. And whenever you see return, you come back here. That's the difference. In jump instruction, there's no return. Maybe you can do it this way. Maybe you can do like a jump, label 1, and you make a label 2 right here. And then you jump, right? Jump to label 1, and you execute each of them. And at the end of it, maybe you can make another jump, label 2. Then you can jump back. Maybe you can do this. I mean, this is not a good way. Nobody probably want to do this, but you can do this way. I mean, you can do it this way. But in call instruction, you want to do this way. Call label 1, then you jump to label 1, and whenever you see return, then you come back. So now let's compare the difference between those two. Let's use a call instruction in return, and compared to this one, what if we use a jump label 1 and jump label 2? So what's the difference between those two programs? As I said, I can still use jump here, and jump here, right? I can still use two different jumps instruction to do the same thing. So what's the difference? The big difference is that when you use call return, right? You're going to use stack. That's the difference. Okay, here's the thing. Let's say you execute this instruction. This is call instruction, and it says label 1. So I know where to jump because it says label 1. So let's jump to label 1. Now you just forget this one, right? I jumped already, so forget this one. I execute each of these instructions. And later I see return. And return instruction is simply RET. No operand. Nothing here. Then how do I know I have to go back here? How do I know? Like this one, let's say. Let's say you are reading a book. You are reading a book here. Okay? And when you read a book, maybe you are reading some page, and suddenly your friend asks you a question. Okay? Please, tell me this one. So suddenly, you actually you talk to your friend. Okay, talk about some of the questions, some of the problems. Okay, and finish the discussion. Now you want to come back, and you want to continue to read, right? Then, since you already discussed so many minutes, so many hours, you forget, right, where I stopped. Okay, in that case, what do you need to do? You probably you probably go back and read from the first page. But that's not a good way, right? You want to go back where to stop, right? You stopped right here, and you want to go back right after that, so that you want to continue reading. So how do you know whether I should come back here or here or here? How do I know? Because this one doesn't tell you anything, right? This one just say return. Return your home. I don't know where is my home. This is my home, but I don't know where. So that's why in this call return instructions, you need to use a stack. So let's see, this is how it works. Actually, before that, there's one thing very important. What is this one? Program counter, right? Program counter. This is a register. What kind of value do you have in program counter? What is the value here? You have a value here in the register, right? So what is that value? Let's say I have a value 100. Then what does that mean? The value inside the program counter will tell you the next instruction. Okay, so this value will tell you what is my next instruction. This one tells you the address of next instruction. Okay, what this means is actually this is next slide, but let me tell you what this means. Because this is all, when you actually do the lab, right, using the emulator, you want to look at the value here. Every time you look at this kind of value, you need to be careful, okay? You have to watch what this value, how this value changed. So let's say this is I said originated 100H, so this is my starting point. That's 100H, right? Since I said here, I started from 100H. Let's say I execute this one. So when I execute this one, okay, this is my first instruction. So when I execute this one, what would be the value in program counter? When you execute this, then program counter will have the value 103. Okay? One thing that remember is that some students think that program counter may have 100 because this is my instruction, current instruction, but that's not true. Program counter will tell you what is the next instruction, okay? So address of next instruction will be in the program counter. So when you execute this one, then program counter will have this value. And when you execute this one, now I'm moving to next instruction. And whenever you go to the next instruction, 105 goes to PC. Remember that the pipelining, right? We talked about pipelining. What was the first step in pipelining? Fetch. And then decode, right? When microprocessor fetch instruction, okay, whenever you fetch, then program counter moves to the next. From the microprocessor point of view, microprocessor will read this one first, which is fetch, right? Whenever the microprocessor fetch this instruction, then program counter automatically incremented to the next one. And after the fetch, now microprocessor will execute and write back. After write back, I'm going to fetch this second instruction. Whenever I fetch this second instruction, then the program counter will again increment it to the next one. Okay? So when the time of execution of each instruction, the program counter has the value of next instruction address. Okay? Remember that. The program counter will have the address of your next instruction. Now then, come here. Now this is my program. I have this program, I execute this line, this instruction, and this instruction, and this instruction. And then I'm gonna execute this instruction, which means that I already have fetched this instruction, and then I'm trying to execute. At that point, right, I'm trying to execute this one, and at that point, what value do you have in program counter? Let's give an example. This is 100, 102. Maybe this is 98. What value do you have? Let's say by I'm trying to execute this instruction, then at that time the program counter has 102. When I execute this one, this goes to program counter. Okay? But what happened is this actually is call instruction. Right? Let me move back a little bit. Let's say let's think about this one first. I execute this one, and this is my current instruction. I'm trying to execute move instruction. When I try to execute this instruction, my program counter will have this value, 100. Right? And I execute this, no problem. And since this is a move instruction, my next instruction is this one. So how do I know which one is my next instruction? I just look at this one and read this value. And this one tells me what is the address of my next instruction. So simply I read it. Oh, 100, that's the address of my next instruction. So now let's move to 100. That's what happened, right? And I move to 100 and fetch the instruction. Then automatically this program counter is now incremented to 102. Okay? And I'm trying to execute this one. And what happened is this is actually special instruction called special instruction say call. Right? So this is a call instruction. What happened is I'm not going to move to next one because this is call instruction. What I'm doing is actually jumping to this. Okay? Then let's say this one, as an example, let's say this one has address 200. This is a 202. I mean, just an example. Then what happened to this one? This one should be changed because this one basically tells you what is my next instruction. And this is not my next instruction in this case because I jump. So what happened? Whenever you have a call, now what happened is that you're going to change this value into 200. Suddenly, this guy changes this value to 200. Okay? And then after you execute, now you are trying to move to next instruction. And what is the next instruction? Go there and read it. Oh, 200, that's my next instruction. So that means I need to jump. That's how you jump, right? You are not jumping. You are changing this value. That means jump. So you are changing this value into 200. So you jump to 200. So you execute this one. And when you execute this one, this value now becomes changed to 202. Okay? So just one by one. Now, let's say at the end of it, let's say this is a 210. At the 210, you see RET instruction. Return. And this one does not say anything, where to return. And when you execute RET, what would be the value in program counter? 212, right? Because the 210 is the address for RET. I guess return is just 1 byte. So next instruction probably is 211, I think. Return probably is 1 byte. So next instruction is probably 211. So when I execute RET, this program counter is indicating the next instruction address. But actually, this is not a regular one. This is a very special instruction called the return. So I need to jump back. Now we have a problem. I lost this one. This is gone. Because when I jump, I change this value. So this value is no longer available. So I lost this one. So I cannot jump. Okay? We know the whole history, but microprocessor is very simple, right? Microprocessor does not remember anything. So how can you jump back? In this case, there's no way to jump back because you lost everything. That's why, let's go back here. When I execute call instruction, okay, at that time, my program counter has the value 102, okay, when I execute this one. Before jump, okay, when you jump, what it means is you are writing this value into 200. Before you do that, you have to keep this in somewhere because I want to keep it. I want to use it later. So you have to copy this one into somewhere. Where to copy it? You copy this one to stack. Okay, put this value into stack. How do you do it? Push PC. When you do this, right, 102, this value now goes to stack. Inside the stack, the value goes down here. And whenever you run the push, your stack pointer becomes incremented, right? Remember? Whenever you do push, like a stack is like a box, right? Whenever you push the value, the bottom will be incremented. Okay? So stack pointer is automatically incremented. Now you copy this value in here. So once you copy it, now you go ahead and change this one into 200. And now you jump it and just move forward. And whenever you say return, okay, what do you need to do? You want to do pop PC. So when you execute return, your program counter actually has the value of 211. Okay, at the time you execute RET, your program counter has this value, but this return basically do the pop PC, which means that you pop this value out and copy into PC. So therefore, because this instruction is return, we are copying this value and back to program counter, which means that we are jumping back to this. Okay? So basically, simply speaking, before you call, before you jump, you copy the value in the program counter into the stack and keep it there. And you run whatever you want to do until you see return. And when you see return, you pop the value from the stack and put that into program counter. Once you do that, then you jump back to your home and you keep going. Okay? So that's what happened in the call and return. And that's the difference. In jump, regular jump, you are not doing it. You are not using stack. You're not going to do anything. But in call and return, push and pop happens. And nice thing about this one is that you don't have to do it. Okay? This push PC and pop PC, you are not doing it. Okay? I didn't do anything, right? I cannot do anything here. What I do is that I just say call and I just say return. That's all I do. Hardware, okay? This hardware, microprocessor, do a push and pop automatically. I'm not doing anything. Hardware do it. Okay? But the inside of hardware, the microprocessor actually doing push and pop. I don't have to do it. This is automatically done. So that's another nice thing. Hardware do it. Example here. 100H. What is this one? Let's look at the first line. What is this one? I'm basically saying that I copy the 76H into stack pointer. What is this one? Once I do this, what this means is that I have a box called the stack, and the bottom of my stack is this value. So 76 is my base address of my stack. Okay? Stack pointer is basically pointing the bottom of stack. So you have to define this because the program, the microprocessor doesn't know where is your stack. You have to define where is the base address of your stack. You have to define it. Microprocessor doesn't know anything, right? You have to define, you have stack. If you need this one to use a call because you are using stack. In the previous like jump and in the simple instructions, we haven't used stack before. Okay, this is the first time you start to use a stack. But when you use a stack, you have to define stack pointer. Once you define the stack pointer, this is the bottom of my stack, then you can use a stack. So you have to define this stack pointer. You define the stack pointer here, and I call subroutine 1. And subroutine 1 is my label. When you execute this one, what would be the value in program counter? When I execute this, what value do you have? 105. Okay, you have a 105 when you execute this. Now this is a call instruction. So when you execute this call instruction, what this guy does, what the hardware does, hardware basically copy the value in here, which is 105, copy this 105 into where? Huh? Stack where? Yeah, tell me the address. You need to know exactly what happened, like this one. This is like a meter, okay? You have to know exactly what value you have, and you're going to copy this value into stack. But where is the stack? 76. So 105 here is now copied to 76, right here, in this case, right? Because this is my bottom of my stack. Once I do that, then what happened to stack pointer? This value now is what? Is incremented because I push one value into stack, and I have 105 into 76. So program count, the stack pointer is now incremented to 78. Why? Because my value in here is 2 bytes. 105. I said 105, right? This is 2 bytes. 2 bytes, right? Not 1 byte. You need the 2 bytes to keep this value. So 2 bytes goes to here, 76, 77, right? So stack pointers now becomes 78. And also the program counter will be also changed to 107. Because this is call. We have to jump, right? So that's all happened. When you see this one, that's all happened. This 105, original 105 goes to here. Okay, and those are 2 bytes. Therefore, the stack pointer is incremented to 78. And the program counter now has a new value of 107. So you jump to 107 because that's where we have in subroutine 1. Now then, go jump to here, and now it's time to execute this one. Okay, when you execute this one, suddenly program counter is also now changed to 108. And then you keep going like that. And there's a loop actually, so you do loop like this. And after you loop, this is a decrement J and Z. So whenever your condition is met, then you loop. And then when the R0 becomes 0, then you go out to the loop, right? And whenever you have return, now when you execute return, the program counter probably have the value of 11E. Okay, 11E probably is there when you execute return. But when you do this, right, the hardware, look at this one, and this is actually return. So what happened? This one now go there in the stack and pop this value out and copy into program counter. And what value did we have here? 105. And now 105 is copied into program counter. Okay? And what happened to stack pointer? It's decremented back to 76. Okay? Stack pointer now decremented back to 76. And now the program counter has a new value of 105. So therefore, we are jumping to 105. And then moving, keep moving like that. Okay? So that's all that happened. So you need to know exactly what happened in these things. These are the registers. And you execute like add R0 and all these things, right? Then you probably have a value in A and R0. These values will be updated. But whenever you do a jump and call, return, and all these things, you probably have the value in P1 counter, stack pointer, and the value in the memory. Those are changed. So everything is changed. Whenever you run line by line, all this value will be changed. You need to know exactly what happened to each of them. Okay? Another example, maybe a little bit more complex. But now, another thing that you look at here is actually a mapping between your assembly code and binary. Okay? Look at here. Whenever you see originated 100H, what this means is that the next line will become 100H. Like this, right? This is directive, one of the directives. So this directive tells you that, okay, my program here will be downloaded into 100H. That's what this means. This first line, move SP 76. That's the that's basically, simply speaking, that's a setting of your stack pointer into 76. And when you change, when you convert this one, when you run the assembler will convert this instruction into binary like this. See that the value, the operand is still there. And this value, this one actually is there. And why do we have these three? I mean, this one looks like a simple, and we have three of them. Why is that? This value still here. Stack pointer, what is the address of stack pointer? Stack pointer has its own address, which is 81. 81 is the address of the stack pointer. You look at the second week of lecture notes. You remember that there is an area called the special function registers. Inside the special function registers, there are some gray area and there are some registers defined. When you look at those things, right, all of these registers we use, stack pointer, A, P1, R0, all of those registers have its own address. And stack pointer has the address of 81H. And move in this case is like 75. That's how you map it. That's what the assembler does. Let's look at this one then. We have an instruction called move accumulator 55. Let's run the assembler for this particular instruction. That's this one. This is only 2-byte instruction. We have a 55 operand still here. And move A, comma something, that's 74. Let's check if that's true. Move accumulator, comma something, that's 74. So let's see here. Let's see, 74. 74. This one, right? Move A something. Okay, so that's how you map it. So come back here. That's how you change between these two. If you know this one, then you can manually, you can convert this one to this one. Or you can do it the other way. Same way. This one, you change it to binary, that's going to be this one. Okay? So you want to, you need to be able to map it between these two. Sometimes it's going to be 3, each instruction, sometimes it's 2 bytes, some other times 3 bytes. Or sometimes, for example, return, it's just 1 byte. Okay? Sometimes 2 bytes, sometimes 3 bytes, sometimes 1 byte. Okay, now let's see. The first line, we are setting the stack pointer. This is my bottom address of my stack. I copy the value 55 into A and copy that value into port 1. Let's call delay. When you execute this one, when you execute this line, program counter has the value of 10A. 10A was there. But suddenly, since I do a call, this 10A is copied to 76. And remember, this is 10A, so therefore these are 2 bytes. So stack pointer will be incremented to 78. And 10A goes to here. Now you may want to ask a question. Since this is a 10A, we have a 2 bytes, 01, 0A. Is it like a 01, 0A or 01, 0A? Which one is that? That depends on the Indianness. Remember the Indianness, like a big Indian, little Indian? If this process is a big Indian, then 01, 0A. Little Indian, the other way. Okay? Let's say here, we were here, and when you execute this one, the 10A was here. 10A was here in the program counter when you execute this, right? And hardware, since this is a call instruction, hardware basically copy this 10A into these 2 bytes, and stack pointer is now incremented to 78, and suddenly you jump to delay, which is this one. And this one has the address of 300. Actually, before you jump, right, you copy 10A into here, and stack pointer is incremented to 78, and also write this 300 into the program counter. So therefore, you jump. And you jump. There's a loop here, so you do loop like this. Actually, this is a, look at this one. This is a loop by itself. It's jumping to itself, right? It's jumping to its own. Keep jumping. And later you have return. Whenever you have return, now you are copying this 10A back, 10A back to the program counter, and stack pointer is now decremented back to 76. So once this value 10A copies to program counter, that basically means that you are jumping back to 10A, and keep moving. And when you have a second call, second subroutine, so same thing happen again. Let me ask you one question here. What if let's say you have this code, you have your own code, and I say call ABC. This is my function, subroutine, and I have some ABC function here, ABC subroutine here. And whenever I have return, then I come back here, right? But let's say I have another call here. Inside the subroutine, I have also call DEF, and my DEF is somewhere else. And I have return. In this case, what happened? This is my main program, and I call the subroutine, so therefore I jump. And inside the subroutine, I have another subroutine. Then I come back. So in that case, what happened to stack? In that case, your stack, right? This value, actually this value, before you jump, this value goes to stack. Let's say stack is like this. This value, before you jump, before you call, this goes to stack. And stack pointer is incremented. Okay, and then you jump, and moving forward, there's another call. So you again push. So this value, the next one, this one, right? Again go to stack. So stack is incremented this much. Then go there, and you keep doing it. And whenever you see return, stack is what? Last input, first output. This is the first input, that's the last output. Last input, first output. So whenever you see return, this one comes out first. That is actually this address. So whenever you finish this one, you jump back. And when you pop this out, the stack pointer has to be decremented to this one. So you move forward. Whenever you see return, then now you pop this value out and jump back to here. Okay? So it's called like a nested jump. So that is also possible. Okay? Yeah, so this is a pros and cons of using subroutines. But you can just try to read this. I mean, this is not a big deal. What it says is that whenever you write a program, you can write a big program. You can put everything in the one program, and your program is like 1,000,000 lines. That's one way of doing. But better way to do it is that you are breaking this big function into very, very small functions. Each one is a very simple thing, like 1 + 2, something like this, right? And you are breaking this whole thing into many functions, and each one is very simple. And in the main function, what you're doing is that you just call the H subroutine. Okay? Main function is not doing anything. Actual operation is done in each subroutine. You are just simply call. That's a better way to do it. That's what it says. Why is that? First thing is that is the readability. What readability tells you is that it's easier to read. Whenever you have small functions, it's easier to read, and it's easy to debug. Okay? That's a better way of programming. But that's actually a better way. Everyone does that. No one is going to write like 1,000,000 lines of code, right? You want to write a code, then you want to make a modular. That's called a module. Each one is a module. You want to do a modular design. But what is the bad thing about that modular design? You make thousands of subroutines, and main function is like small. You just call the subroutines. What's the bad thing about it? Think about it. What is bad? Generally, it's very good, but there's one problem of that. You want to remember the word called context switching. This is a very common word, especially for software design and also some hardware embedded systems. You sometimes hear context switching. What this means is that, let's say, if you have 1,000 lines or 1,000,000 lines in your code, then you probably don't need a stack. Maybe you need some stack, small stack, but generally you don't need to have a stack. But let's say you have thousands of subroutines, and you have to jump to a subroutine and come back, and sometimes subroutine, and inside subroutine you're jumping to another subroutine. Okay? Once you do this kind of thing, right, then you need to have a bunch of stack. And not only that, whenever you do a jump, what do you need to do? You have to copy this value into stack, and also your program counter, you copy to new value. Stack pointer also has to be incremented. Those things has to be done every time. Every time you jump, every time you call the subroutine, you have to change all this value. Every time. That's context switching. It's like you have one context, suddenly you are switching to another context. You are in the main program, you're suddenly switching to a subroutine. That's another context. So that's called the context switching. And every time you do a context switching, you have to change the stack pointer. You have to push some value or pop value into stack. So you have to manage the stack pointer and also the contents of the stack. So sometimes that is actually not a simple task. That requires a lot of work. Right? So that's a little bit bad thing. You have to do a lot of context switching. Every time you do context switching, this is some work. However, still, this kind of modular design is a better way to do a programming. For us, we don't worry about the stack, right? Hardware do it for you. You don't do it. So it's a work, but hardware do it, so I don't care. So generally, it's a better way to do modular design. Any question? Okay, see you Thursday.